Hello everyone, we are from Team ColdFire and the team members are Amit, Prithvi and Shailesh. We have implemented a secure network processor and we are going to give a short demonstration video on why our system is relevant in today's world and how it works. Cloud computing is gaining popularity these days, mainly because the user do not have to worry about setting up and maintaining a huge system. Cloud computing can be broadly classified into three categories, such as software as a service, platform as service, infrastructure as service. But the biggest question is how secure is our data at the cloud? Let us see an example for that. Almost all the cloud systems today have security inbuilt to them, but only at the software level. Suppose an insider has an access into these machines and able to probe the memory, he might be able to understand what's happening inside there and he might selectively modify particular data and this might result in catastrophe. To resolve this security issue, we have designed a dual core system as shown. The first core acts like a front end to our system and handles tasks such as packet processing and key exchange. The second core is a secure crypto cloud engine. Every piece of memory in this core is completely encrypted by the symmetric key provided by the host. And this symmetric key exchange happens through RSA encrypted packets. Hence, the whole system is completely secure. Let's look into working of our cloud system. Our Verilog files are synthesized in Gen 6 servers at ISI and the bit file is generated. We have laid out a small network topology in the data lab to verify our system. And this window represents the control node of the NetFPG in data lab. These two are the nodes representing host and the cloud system. And we'll use this window to capture the packets leaving and arriving at the host. First step is to set up our cloud system environment. Here, our NetFPGA's network interface is configured and we load the bit file generated through Gen 6 server into our NetFPGA. We have already compiled the binary file for the front end core of our system. Let's just load it. This Perl script basically has bunch of software registers embedded into the system. It accesses it and writes into the iCache of the first core. Now let's enable the PC for the first core. Program counter is now enabled and the system is ready to go. Let's check by pinging into cloud system, which is node N1. The system is ready to go. Before going any further, let's look into some of the software at our host side. We have implemented a compiler for our custom ISA using Perl. This Perl script converts any C code into MIPS assembly language and then to our custom ISA. It can also generate encrypted binary output to be sent to the cloud. The code to be sent to the cloud is encrypted using symmetric key. It uses symmetric key to encrypt the channel between the host and the cloud. Let's change this value into some new arbitrary values. Let's say host want to run a bubble sort code in our cloud machine. Here is a sample C code for a bubble sort program. We can see values 7, 2, 9, 5, 4, 1 in this particular order and these values need to be sorted. Let's compile this code and get a encrypted output using our compiler. We have a completely encrypted instruction set to be run on the cloud is ready, and let me copy this value and transfer it into our host at the editor. Let's go back into our cloud environment. Before sending any packet and starting the transaction between the host and cloud, let's set up a server at the cloud. Now cloud can receive UDP packets from any hosts. Let's also set up a TCP dump at host side to capture all the packets coming in and going out. Host now sends its public RSA key to the cloud machine over ICMP packet. Cloud machine receives this packet. It encrypts its own public RSA key in public RSA key of the host and sends it back. We can see that this ICMP packet has been modified by the cloud, and the last 8 bits of this data word contains the encrypted public key of the cloud. Next, host sends a symmetric key to the cloud, which is encrypted in the public RSA key of the cloud. This key will be used to encrypt the channel between the host and the cloud. Henceforward, all the packets which are sent from host to the clouds are encrypted with this particular symmetric key. Hence, the channel is completely secure. Then the host sends instruction symmetric key in which all the instructions to be executed in the cloud machines are encrypted. And note that this key is also encrypted in the channel symmetric key. Host now sends the encrypted instructions which we have generated earlier for the bubble sort code over here. Based on the size of the code, the instructions are split into multiple UDP packets and are sent to the cloud. We can see that this bubble sort code is split into 24 UDP packets and are received by the cloud over here. Once the last UDP packet has been received by the cloud, the front-end core of the cloud machine enables the crypto engine. All the encrypted instructions are executed here. Then the host sends a request for the result in particular memory locations, and the encrypted results are obtained. Let's look into the authenticity of the result what we have obtained. Quick sneak peek into the bubble sort code. We had data in this order 729541, and once it is sorted we should get back 124579. The result what we have here, that is this particular field of the ICMP packet, is encrypted twice, once in instruction symmetric key and once again in channel symmetric key. Hence, XORing this value once with the channel symmetric key and once with the instruction symmetric key, we will get back the result. We can clearly see that this particular value is 1 and the next memory address is 2 and the third memory location is 4 and fourth memory location is 5 and fifth memory location is 7 and the final memory location is in fact 9, hence proving the correctness of our implementation. Thus, we have successfully implemented and demonstrated the concept that a crypto engine can be completely encrypted, that is, including instruction cache, Tcache, as well as register file. Hence, such system can greatly enhance the security of cloud systems. Thank you.